So this one is a weekly pop quiz 13, the MCQs pop quiz. You can ask your doubts if you have in question one. Any doubt? Question one. Question two, any doubt? Question three. Question one, there's a doubt. Okay. So in question one, a body of a mass m, which is moving with a velocity v, it collide with a stationary body of a mass m. Which would describe the momentum and the kinetic energy of the two bodies after the collision? So the mass m is there and it is moving with a velocity v. It collide with a stationary body of a mass m, same mass. The two objects have the same mass. And the second object was stationary in the beginning, so its velocity is zero. Then the two objects stick together. If the two objects stick together, it means the mass is double. So for a momentum to be conserved, so if the mass is double, what will happen to the velocity? The velocity will become half. Because if the momentum is conserved, the total momentum before should be equal to total momentum after. So if the momentum before is, this was mv and this one is zero. So momentum after, as the two objects stick together, so mass is double, so the velocity should be half. Means each will have the same velocity, but or compared to original value, it should be half of it. So the momentum of this one will be mv by 2 and the momentum of this one will also be mv by 2. And when we add them, the total momentum will be mv. So the momentum before should be equal to momentum after. So the question is, which row describe the momentum and the kinetic energy of the two bodies after the collision? So after the collision, because the momentum should be conserved, even if it's a collision is elastic or inelastic, momentum should be conserved. So the momentum should be mv. So either A can be an answer or B can be an answer. But what about the kinetic energy? The kinetic energy, as we want the kinetic energy after, describe the momentum kinetic energy after the collision. So what is the kinetic energy after the collision? The kinetic energy of the first object, it will be half mv square. But what happened to v? V become half, so we can say it will be v by 2 square. And what happened to the mass? The mass is double, so I can write as separate, like half mv square for the first object and then half mv square for the second object. And then I will add them. That is one way of doing it. Mass is m, velocity is v by 2, and mass is m, velocity is v by 2. When we simplify this, it will be half mv square by, because 2 square is 4, plus half mv square, and 2 square is 4. When we simplify, this will be mv square by 8. This will also be mv square by 8. When we add them, 8 will be the LCM. So it will be mv square plus mv square. So it is 2mv square. So 2mv square by 8. When we further simplify, it will become mv square by 4. So the kinetic energy after will be mv square by 4 or 1 by 4 of mv square. So that's why it matches with option A. So A should be the right answer. Is it clear? So whenever two objects are colliding with each other of same masses, if the two objects stick together for a conservation of the momentum, then velocity is becoming half. Question 2, any doubt? Question 3, any doubt in question 3? Question 4, question 5, question 5. An ice hockey puck slides along a horizontal frictionless ice rink surface. It collides inelastically. If it's an inelastic collision, it means the kinetic energy before is not equal to kinetic energy after. So it collide inelastically with the wall at a right angle to the path and then rebound along the original path. Which graph shows a variation with time for the momentum of the puck? So what will happen? See, if we take the mass is m, let's say it was moving with a velocity v, then it hits a surface and it inelastic collision is there. The term inelastic means the kinetic energy before will not be equals to kinetic energy after. Means the velocity will change. And definitely when the objects collide, it loses its energy. So the what will happen to the velocity? The new velocity, let's say this velocity was v1 and this velocity is v2. So v2 will be less than v1. And the second thing what happened is the direction also changed. So if the direction has also changed, if one of the direction we took as positive, the other will be negative. So two things will happen. Number one, the momentum will change, the value of the momentum will change, and the second thing what should happen, the direction of the momentum has also changed. So how we'll know the direction change? So if a direction of a vector quantity has changed, so we should use the momentum is plotted on y-axis, so we should use the positive and the negative values. Because if the direction change, so which axis we are using positive and negative? So we are using either A or B, we are using it, but we are not using in C and D. C and D, we only use the same axis, like same positive axis is used. It means the magnitude has changed, but not the direction. If the direction has changed for a vector quantity, the positive direction will use a positive y-axis. For a negative direction, we'll use a negative axis. So means it cannot be C or D. That's totally wrong. We are left with A and B. Now what happened, as they mentioned here, it is moving with the velocity and it rebound. So the velocity was not changing. As in the question, they did not mention, it's mentioned here, it's a frictionless. So what this give an indication if it's a frictionless, so it means it is not slowing down or it does not reduce the speed. If it was a not a frictionless surface, then what will happen? This velocity will also decrease initially. But because it's a frictionless, so the velocity will not decrease. If the velocity will not decrease, the product of the mass and velocity will remain constant. So that's why the product of a mass velocity remain constant. And when it rebound, the velocity, the new velocity is smaller or than the first one. So the direction has changed, but again, the velocity will not change. So the product of the mass and velocity will be constant. So we'll use both axes, positive and the negative axis, which shows the direction has changed. And why the momentum was constant? Because it was a frictionless surface. Mass of an object is constant until unless it move at a relativistic speed, which is this close to speed of light. And the velocity can only be changed if there is a friction or a drag in the surface. So the correct answer for this one is A. Is it clear? Question 6, any doubt? Question 6 and 7, okay. A ruler of a length 0.3 meters is pivoted at a center. Equal and opposite forces of a magnitude 2 newtons are applied to the end of a ruler, creating a couple. How we calculate the moment due to a couple? Moment due to a couple is a force multiplied by distance between the forces, but the perpendicular distance between the forces. A force is given at an angle of 2. So if I draw this, what will be the angle? Because we always need a perpendicular distance and the perpendicular component of the force. So if we say this was a force, the component of the force which we need, and same way here, this is a component of the force which we need. And the total distance between the force, they mentioned the ruler is 0.3 meter. So this one is 0.3 meters. Now, if this angle is 50, how much is this angle? Because the perpendicular total angle is 90, so this will be 40 degrees. So if this is 2, the component of the vector which is with an angle, that is always written with cosine. So what is this component? So this will be 40. This will be 2 cosine 40. What about this component? Here this angle will be 40 because total should be 90. So this is 40 degrees and the vector is 2. So the component which is with an angle, so what is this component? So this will be equals to 2 cosine 40 as well. So what we do, we just take the force, any one of the force and the distance between them. If we want a moment due to a couple, so take any force and the distance between the two forces. So any one force we can take, so it will be 2 cosine 40 multiplied by the distance between them. So the distance between them is 0.3. So when we multiply, we'll get the moment or the turning effect. Is it clear? So correct answer will be C, 0.46 Newton meter. Question 7, any doubt? In question 7, the diagram shows a particle X with a kinetic energy Ek about to collide with a stationary particle Y. Both particles have the same mass. After the collision, X and Y travel onward together as a single particle. How much the kinetic energy is lost? They did not ask what is the new kinetic energy. They're asking how much there's a loss in kinetic energy. If you remember question 1 when we did, it's the same question, but they asked what is the new kinetic energy. But now they're asking how much the kinetic energy has lost. So if we consider this was moving at a velocity v, the mass is m here, this was stationary. The kinetic energy for this particle is Ek, which is actually equals to half mv square. When the two objects stick together, the two objects of the same mass stick together, move in the same direction. So because if the mass is, this mass is m and this mass is also m. Momentum should be conserved, first thing, because in collision, any kind of collision, even elastic or inelastic, the momentum should be conserved. So for a momentum to be conserved, if this momentum is zero and this one has a momentum of mv, so this should also have a conserved momentum, like the sum of the momentum of the two should be equals to mv. That's why this object x will move with the velocity v by 2 and object y will also move with the velocity v by 2. How, like they will move together with the same speed. So what is the kinetic energy after? So the formula for kinetic, we did this same thing. Kinetic energy is half mv square. So it will be v by 2 whole square. Plus kinetic energy is half mv square. So v by 2 whole square. When we simplify this 1 by 2, it will be mv square times 4 plus 1 by 2 mv square times 4. So when we simplify this, it will be mv square by 8. This is also mv square by 8. When we further simplify, take an LCM, 8 is LCM, mv square plus mv square. So this will turn out to be 2mv square by 8, which is mv square by 4. Or if we compare what happened to the kinetic energy, like how much kinetic energy is lost. So how much kinetic energy is lost? This is the original kinetic energy, half mv square, and this is the new kinetic energy. So if we need a loss, so it will be half mv square. You can also write in terms of Ek, because we know, like if I can further simplify this formula, mv square by 4 is equivalent to what? It is equivalent to half mv square times 2. And this half mv square is what it is equals to Ek. So means this kinetic energy is Ek by 2. Compared to original, this is half. The question is not what is kinetic energy after, the question is how much is lost. So how much is lost? So originally it was Ek and now it is Ek by 2. So when we subtract them, if 1 minus half, so we'll get half of it. So it will be Ek by 2. So C will be the right answer. Is it clear? Question 8, any doubt? Question 9. Question 8. The diagram shows two identical spheres, x and y. Sphere x move with the speed v directly towards y and y is stationary. The sphere collide elastically. If there is an elastic collision, two things should happen. Number one, the momentum should be conserved, and number two, the kinetic energy should also be conserved for elastic collision. So we have to check the statements, which statement explain the collision to be elastic, because momentum should be conserved plus the kinetic energy should also be conserved. If what is the kinetic energy before? This is a stationary object. If we take this as mass m, they have identical spheres, so both have the same mass. So kinetic energy will be equals to half mv square. So Ek, or the kinetic energy, equals to half mv square. Now, the second thing, first thing what we do, we always check for momentum. If momentum is conserved, then we check the kinetic energy. So if A was the right answer, move with the speed v by 2 to the right and move with the speed v by 2 to the right. Means they will both move with the same speed. If the two objects stick together, it means they stick together. If two objects stick together and they move with the same, like half of the speed, so what will happen? The momentum is conserved, because when I sum the momentum, it will be mv by 2 here, and this will be mv by 2. So mv by 2. So when I sum, I'll get mv. Momentum will be conserved. But what about the kinetic energy? We did that just now, that the total kinetic energy, when we add the previous part, it was ek by 2. Like it will become half of the original. When you add the kinetic energy, half mv square for this one and half mv square for this one, the total kinetic energy will become half of the original value. So means in this one, momentum is conserved, but the kinetic energy is not conserved. When we check the second option, move with the speed to the left and remain stationary. This is impossible. Why it is impossible? This is not at all possible. Why? Because what is the total momentum? The total momentum was mv, which was towards the right hand side. According to a conservation of the momentum, once the objects will collide, they should have the same momentum in the same direction. The direction of the momentum, the total net direction of a momentum should also be same. But if the v move in opposite direction, so the momentum of the x will become minus mv, and this is remain stationary. So as a result, what will happen? It means the total momentum is not conserved. Why? Because here the original momentum is towards the right hand side, but after the collision, the momentum is towards the left hand side. So which shows that the momentum is not conserved. So B shows the momentum is not conserved, so we will not move to check the kinetic energy. What about C? Move with the speed of a half to the left and move with the speed half to the right. So that is also impossible. Why? Because the initial momentum which is mv, so the final momentum should also be mv. If x is moving towards the left and y is moving towards right with a half speeds, v by 2 here and v by 2. So what is the momentum here? It will be mv by 2. And what is the momentum? Minus mv by 2. Or if you take this plus, this will be negative. So when you take the total momentum will be 0. So momentum is not conserved, because before and after the momentum should be same. When we check the last option, x is stopped and y move towards the right. So x has stopped, x is not moving, and the y is moving towards the right hand side with a velocity v. So momentum will be conserved, and the kinetic, because momentum will be 0 plus mv, and kinetic energy will be half mv square, and the kinetic energy will be half mv square. So it means the both momentum and kinetic energy are conserved. That's why option D should be the right answer. Is it clear, this one? Question 9, any doubt? Question 10. Question 11. Question 12. Question 12, okay. In question 12, a 1.2 kg mass is supported by a person, hands, and 2 Newton meters as shown. When a person's hand is removed, what is the initial acceleration of the mass? So the weight is acting downward, which is 12 Newton. What is the resultant force of these two Newton meter? Because this total angle is 37 plus 53, which will make 90. So if we have two vectors which are perpendicular, like one of them is 3 Newton, another one is 4 Newtons. So if two vectors which are perpendicular, what is the resultant of the two vectors? We can use a Pythagoras theorem, 4 Newton and 3 Newton. So what will the resultant? So resultant will be 4 square plus 3 square. When two vectors are perpendicular directly, you can use a Pythagoras theorem. So 4 square is 16, 3 square is 9, 16 plus 9, 25, and root 25 is equals to 5. So means the resultant of these two forces is equals to 5 Newton, which is acting. The resultant of these two forces is 5 Newton, which is acting upward. But the weight of this mass, this object, is acting downward, which is 12 Newton. So we need the acceleration. F is equals to ma. But this F is the resultant force. So what is the resultant force acting the moment a person remove the hand? So when a person remove the hand, what will happen? The 12 Newton downward and a 5 Newton upward. So it create a resultant of 7 Newton. Because 12 minus 5, so that will get 7. The mass is 1.2 and acceleration is unknown. So 7 divided by 1.2, what's the answer for this? The acceleration of this? So we got 5.8, or we can say 6 meter per second square. So it's the same idea. It's a force triangle. You can also make, like, first you have a 3 Newton, then you will have a 4 Newton. If you draw the 4 Newton here, this will be 4 Newton. So what will the resultant? The resultant is from tail of the first to the head of the last. So even if I make a triangle, I'll get the same result. So this will be 4 Newton and this is 3 Newton. The angle between, whenever angle between the two vectors 90, I can simply work out the magnitude by using a Pythagoras theorem. If they ask for direction, then we will use the trigonometric ratio. But if we need the magnitude, we can just use a Pythagoras theorem. Why did we not use sine or cosine? Because we were not having both. If you want to use a sine or cosine, you can use sine or cosine. Then you will divide the force into components. Look, what will be the component? Let's say this is a 3 Newton force. Okay. So this is a 3 Newton force. What will the component here? So this component for 3 Newton force, this will be equals to 3 cosine 53. And this is the 4 Newton force. What will be this component for the 4 Newton force? So this will be this component here. That will be equals to 4 cosine 37. So what is the total force upward? So that will be equals to 4 cosine 37 plus 3 cosine 53. That will be the total upward force. And when you sum them, you will get the 5. So it will work with the same manner. Even you divide the force into components and like resolve the force into the rectangular component and sum the rectangular component in the vertical plane and then subtract from the 12 Newton, you'll get the same resultant force. It won't make difference. Because the angle was 90, that's why I directly use that. If the angle, let's say the angle was not 90, let's say this was angle was 30 and this angle was 50. In that case, I cannot use a Pythagoras theorem. Then I'm just constrained, like a limitation, that I have to resolve the force into the component. Because the angle was 90, so it makes it very simple to get the resultant when it's 90. Question 13, any doubt? Question 14, any doubt? In question 14, an object of a mass m is resting on the top of a spring. The spring is compressed. So when we compress the spring, which form of energy it will store? It will store elastic strain energy. And how we get the elastic strain energy? The elastic strain energy is half force into extension. So the total energy stored is elastic strain energy. The moment we release this mass, like this spring will stretch. So spring is moving the object. The spring is moved. The force is removed. The spring is returned to its original length. The extension becomes zero as the object is at, and the position, the speed at which it is moving is v here. Which of the following equation describe the energy transfer? So what is the energy transfer? Initially, the energy stored is the elastic strain energy. And elastic strain energy is half force into extension, because some of the energy will remain, so it's always force into half force into extension. The second part, when it is moving, because already it's moving, so which form of energy it will have? Kinetic. And because it is raised to certain height, so which form of energy it possesses? It also possesses the gravitational potential energy. And how much is the gravitational potential energy? That is equals to change in height. So if we need a potential energy, this was the starting position and here it moved new position. So it is mgh, and h here is the change in the length or extension. So potential energy is mg delta x. What about the kinetic energy? It's moving at a speed v. So kinetic energy is half mv square. So the total energy will be equals to the sum of kinetic plus potential. So elastic strain should be equals to Ke plus Gp, gravitational potential. So, and kinetic, elastic strain is half force into extension. Why not minus? Because originally it was not having kinetic energy. Originally it was having elastic strain energy. Because the spring was compressed. So you have to understand the energy transfer. What is the energy transfer here? The elastic strain energy which was stored in the spring, that is being transferred to this mass. So it starts to move and it reaches certain height. Like if I say I throw a ball vertically upward. So if I include my energy, then I will say the chemical energy transformed into kinetic plus potential. If it is stop, then it will be kinetic will be zero. But the moment we release it and it is still moving, so it possesses both kinetic and potential. So the input, the stored energy in the spring is a elastic strain energy. So B should be the right answer for this. Question 15, any doubt? Question 15, a student measured a time for a steel ball bearing to fall a measured distance in air. The student used his measurement to determine the acceleration due to gravity. If you want to determine the acceleration due to gravity and we drop an object from certain height, so we use the equation of motion which is s is equals to ut plus half at square. If the initial velocity is 0, if the initial velocity is 0, this whole factor will be 0. So s is equals to 1 by 2 gt square. So what we are doing, either we are measuring a height and the time to work out the acceleration due to gravity. So it will be 2s divided by t square will be equals to g. That's how we get g. The question is, which of the following conditions is needed to determine an accurate value of acceleration due to gravity? If you want to work out the acceleration due to gravity, we don't want the object to reach a terminal speed. The airflow around the ball bearing should be laminar. The airflow, what we want, if we want the acceleration of a free fall, what we don't want air to oppose the motion. Even there are two types of flow of a fluid. It can be a laminar flow or a streamlined flow or a turbulent flow. So we don't want the air to flow around the sphere when it is falling. So we want to ignore the air resistance. So even the flow is a laminar or a turbulent. Turbulent flow means the airflow will be like this. Randomly, the air particles will collide. So we don't want the air flow to be laminar or turbulent around it. We want to neglect that airflow. That's why which of the conditions is needed to determine the accurately. So we don't want air to flow, even it's a laminar or turbulent, we don't want it. The time taken to achieve a terminal velocity should be short. It should not reach a terminal velocity, because whenever we are finding the acceleration of due to gravity, We don't want a falling object to have a terminal or a constant velocity. The ball bearing should be designed to fall before the timer started. That's it's increasing an error in the experiment, because a ball bearing should begin to fall before the timer start. Like when ball is just about to fall or it is falling and then we start a timer, this will reduce the time interval and it will give a higher value of acceleration due to gravity. So this is totally incorrect. Air resistance and the upthrust both should be neglected. That is what we want. We don't want the air to oppose the motion of the ball bearing, and the upthrust is a upward force which the fluid apply. We want to neglect that upward force, because both these forces reduce the acceleration, because upthrust will act upward and the drag force or a viscous drag will also act upward. So both of these forces try to oppose the motion or reduce the acceleration. So we should ignore both of them or neglect them. That's why D should be the valid answer for this. Question 16, any doubt? Question 17. Question 17, student carry out experiment to determine the Young's modulus of a copper. The student adds a known masses to a copper wire and he measures the corresponding extension. Which other quantity should he measure directly? If we need the Young's modulus is stress over strain. How we work out the stress? Stress is force over area and strain is change in length over original length. So if we simplify this formula, it will be FL divided by delta X, you can say, or delta L. It's the same thing, and A. This is how we work out the Young's modulus. So known mass is there, so force is known. Corresponding extension, so extension is also known. So what he has to measure? He has to measure the length and he has to measure area. But area cannot be measured directly. Area is calculated. What measurement is done? We calculate the area either by diameter, pi d square by 4, or we use pi r square. Area of cross section of the wire, pi r square, or pi d square by 4. Even radius cannot be measured directly. It's the diameter which we measure for the wire, and after determining the diameter, we half it to get the radius. And then, so because we need the length and area, so length can be measured directly, but area cannot be measured directly. Area, to get the area, what we need diameter. So we need the diameter and we need the original length of a wire to know its Young's modulus. Even why radius is not correct here, because the radius cannot be measured directly. Radius, if you have a cross section of a wire, you always measure a diameter, and to get the radius you divide it by 2. So the thing which you measure directly is the diameter, not the radius. Radius is half of the diameter, so radius is calculated, not measured. Practically, we measure the diameter rather than a radius. Radius is half of the diameter which we calculate from a diameter. Question 18, any doubt? Question 18, any doubt? Any other doubt in this? So this was a pop quiz 13.